Ladies and gentlemen, welcome to this second webinar-style technical presentation by the Royal Institution of Naval Architects, the Institute of Marine Engineering, Science and Technology and Engineers Australia. The acknowledgement of country. Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises the continuing connection to land, waters and community. We pay our respects to them and their cultures, and to elders both past and present and emerging. Ladies and gentlemen, our presenter this evening is Christelle Auguste, who's a PhD candidate at the Australian Maritime College. Christelle grew up in Brittany, France, sailing on the Atlantic Ocean, and graduated with a master's degree in marine science from the CTEC School of Engineering at the University of Toulon. She then worked for 10 years as a hydraulic engineer with the French National Railway, SNCF. After a sabbatical year in Tasmania, she commenced research for her doctorate at the Australian Maritime College and is the current holder of the Laurie Prandolini Research Fellowship, awarded by the Institute of Marine Engineering, Science and Technology. Ladies and gentlemen, Christelle Auguste.
Hi, thanks Phil for the introduction and for the acknowledgement of country for the last day of the Reconciliation Week. And thanks everyone to join us. So I'm going to present what I'm doing in my PhD about tidal energy and sediment process. So let's begin. So imagine a life without energy. No light, no heat, no cooking, no commuting. Your way of life is defined by energy. With climate change, we need to develop cleaner and sustainable way to produce energy. And you know what? Ocean, who covers 71% of the planet, is an amazing source of power. Tidal energy is one of the most advanced marine renewable energy technology. The economic potential of tidal resources is reliable when compared to other types of renewable energy, like wind or solar, as tide has the advantages of being highly predictable. It can become a great contributor to the energy industry all over the world, as you can see in this map. So the potential of energy generation is most in Canada, then in UK, and after it's between Australia, Asia, and France. There are different technologies for the design of the turbine. Most of them are seabed mounted. Here you can see at the top, it's 3 different types of seabed mounted turbines. The first one is with the company Naval Energy, open in draw, with a round shape. In the middle is CIMEC Atlantis with a single turbine with 3 blades. And the last one is Siemens and CIMEC Atlantis with 2 turbines. The last one at the bottom, it's a floating one. It's another prototype we've developed at the moment with two turbines. There are several projects which are already grid connected with seabed mounted turbine, all in Europe. I'm going to present you 3 projects. The first one is a Medgen tidal project by the company CIMEC Atlantis, and it's happening in Scotland. So they use a turbine with like 18 diameter for the rotor. Each turbine is located on an individual foundation with a weight about 200 tons, and also with 6 ballast blocks with 200 tons as well to provide horizontal stability. So in this area, the current speed is about 4.4 meters per second. And last year, with only 4 turbines, they reached 14 gigawatts, which is the equivalent of the average annual consumption of around 4,000 UK households. And this year, to date, they reached 28 gigawatt, and it's just the first phase with 4 turbines. In the future, they hope to deploy 250 turbines in the ocean that could power about 175,000 homes in UK. And the last news for this company is they have also installed one of their turbines in China just in April this year. The second industry is Nova Innovation with a smaller turbine, and the project is happening in UK too, in the Shetlands. It's a smaller turbine of 8.5 meters diameter with a rated capacity of 100 kilowatts for a current speed of 2 meters by second. The last project is happening in France with the company Sabella, is located near Ocean Island, and they deploy a turbine with 10 meters diameters and for maximum power output of 1 megawatt for a current speed of 4 meters by second. So tidal energy industry is very active in Europe, and it's coming to Australia. According to a preliminary study from CSIRO, there exists promising areas where tidal installations are possible. It's, let me see if I can. It's in Western Australia with King Sound, around Darwin in the Clarence Strait, in the Torrens Strait, and in Tasmania with the Bank Strait. The Austin project, Tidal Energy in Australia, is a project co-funded by RINA, has also identified Bank Strait and the Clarence Strait as promising sites for tidal energy. The goal of this project is to map tidal energy resources and assess its economic feasibility. My project is part of the Austin project and is focused on Bank Strait. People in tidal industry are interested by this site, and they need to better understand all the characteristics in this environment, and one parameter is sediment transport. So why sediment transport is important? Sediment in the ocean can be moved by currents, by waves, and very often by both. Sediment is set in motion when lift and drag forces are greater than gravitational and friction forces. Once the particles are in motion, 2 modes of transport are distinguished. First one is the bed load transport, so the mobile load close to the seabed in almost continuous contact with the seafloor. And the second one, the suspended load transport, the load that is no longer in contact with the seafloor due to turbulent flow higher in the water column. Friction between the near seabed currents and the seafloor creates a layer of shear, increase the turbulence above the seabed. It's the bottom boundary layer. This is the layer where the flow is the most influenced by the seafloor. The effect of currents and waves on the sediment dynamics take place in this layer, and the friction they exert on the seafloor is expressed with the bed shear stress. The bed shear stress is a principal parameter acting on sediment dynamics and is a function of the square velocity. The transport of sediment is proportional to an even higher power velocity. So the total load, which is composed of the bed load and suspended load, is a function of velocity power 3 or 4. So small changes in current speed could lead to large changes in sediment dynamics. And sediment play a crucial role in coastal ecosystem. Sediment movements are responsible for the dynamics of sandbanks. Sediment influences morphodynamics, and sediment movement influences offshore and underwater structure. Placement of tidal turbine in the ocean would increase the flow near the seabed and intensify the friction of sediment. The development of marine renewable energy pushes the scientific community to better understand this natural phenomena and the interaction with the device. Tidal energy is a clean technology and will help reduce reliance on fossil fuel. But it still faces challenges. Which one? First one is the uncertainty about interaction with the environment, like sediment transport. Sediment dynamics have an important implication to local fauna as well as turbine foundation and longevity. The second one, it's the limited full-scale environmental survey, as it is at early stage of development. We've seen earlier there is just few projects advanced enough to be grid connected. The third one is a difficulty to acquire data, especially sediment data, to calibrate, validate the numerical model in this high energy site. And you can notice why it's pretty rough condition over there. So this picture was taken during our first trip in March 2018 in Strait. It was a 17-day trip, and the sea was like this during 3 or 4 days, so it was pretty rough, and I was sick during almost half of the trip. So regulators in tidal industry are particularly sensitive to potential influence tidal energy converter could have on the marine environment. And little is known about regional scale fluctuation in sediment transport in tidal energy sites. Site-specific conditions are crucial for assessment, and for now, no specific study exists in Strait. So to address all these challenges, the objective of my thesis are the following. Investigate the ability and sensitivity of sediment transport model in 2D and 3D to characterize high tidal energy sites. To explore sediment measurement method to determine the best compromise between cost and time with model accuracy. To apply the model to study the hydrodynamics and sediment transport in Strait. And to investigate the interaction between tidal energy converter and the sediment processes for various seabed and for several RS scenarios. The corresponding activity are the following. First is a literature review of the domain, the study of an Idealised theoretical channel, the study of Strait, and to finish, to define guideline and method for tidal energy developer. So first, try to understand the numerical model in an Idealised channel. I'm using MAG21 and MAG3 from software from DHI for all my simulation. So the tidal channel is in the middle. It's 30 kilometers, and it's connected to an open ocean and a tidal bay. Simulations were performed to quantify model ability and sensitivity, like the difference between 2D and 3D, the different sediment transport formula, and different layout of turbine. So for this project, it was just pure current only. So first, I evaluated the model against results from the literature. So I'm using another study from Yang, who used the MHK model. I use the same parameters as him. So 5 cases were performed with turbine in each cell of the tidal channel. So beginning at 1, and then 2, 5, 6 to 9 turbine in each cell. And like this, we were able to compare the simulated extractable power, it's the graph on your right, and compare the MAG model to the MHK model. The model results closely match the MHK model with a maximum difference with less than 5%. So the difference can be explained by the discretization of the channel. I have 10,855 cells in my channel, compared to the MHK, who have only 1,140. So after the validation of this model, I tested different layout of turbine, configuration with fans, and configuration of tidal farm. So A and B are fans, and the C is a tidal farm. I compare current speed and bed stress compared to the baseline. So the baseline is a model is a case with no turbine. And the reduction in current speed is larger for the layout of tidal farm compared to the fans. By example, for the 500 turbine, we reach 6.5% against 11% in the tidal farm. So I took the case with most difference compared to the baseline, which is the 500 turbine in the tidal farm configuration, and I have a look to the bed level changes. So here you can see the difference of bed level change for 3 simulations. So for the 3D simulation, the mean velocity component used as an input for sediment transport rates can be calculated in 2 ways. We can use the depth average velocity, or we can, or the velocity can be derived from the bottom stress value. So for the 2 first one, the 2D and the 3D using the depth average velocity, there is not a lot of difference. The mean difference is about 4%. With the bottom stress value, it's another story. The comparison with 2D reveals an increase of 70 centimeters for the bed level change. So the last model at the bottom captures more accurately the flow around the farm than the 2 other models. It captures the acceleration caused by the construction of the flow near the seabed under the device. That's why a new zone of erosion, like the blue line, appears at the vicinity of the farm. So here we can see like 3D is a powerful tool to have accurate results on the change of sediment dynamics at the location of the tidal farm. But what about regional scale? To answer this question, I created another domain with a tidal channel twice as long as the first one, and it's 60 kilometers. You can notice there is not a huge difference between 2D and 3D far away from the tidal farm. At about 30 kilometers away from the tidal farm, the average difference between 2D and 3D is about 0.37 millimeters. This suggests that for regional scale, 2D seems sufficient. Moreover, 2D models were, in this case, 9 times faster than 3D. So after looking at the spatial extent, I tested 2 different sediment transport formula. It's a formula from Van Wegen and another formula, Engelen and Fretzo. Engelen and Fretzo generated the largest bed level change inside the tidal farm. I'm going to try to show you with the cursor. So here is the connection at the open ocean, here the tidal bay, and in the middle it's the tidal farm. So we have more precise detail in the 3D model. But yeah, Engelen and Fretzo have the biggest change. So I tested for different tidal range to investigate the difference between the 2 formula at different current speed. It's here. So I plotted like the average bed level change against the current speed. And above 1.6 meter by second, the Engelen and Fretzo formula generated a large difference in bed level change. The Van Wegen one in red here generated smaller change, suggesting this formula has a lesser dependency on velocity than the other one. So for this theoretical channel, I was able to create a benchmark for interaction of tidal energy converter on sediment transport. I've shown that MIC 21 and 3 can be used for tidal energy extraction modeling. I've seen that beyond 100 turbine, the impact of tidal energy converter array becomes significant. We've seen that 2D model seems sufficient to assess behavior of sediment dynamics away from the tidal farm, but 3D model using the bottom velocity for sediment transport rate is needed for more accurate result in the tidal farm. And the last thing we discovered is that there is a difference of 1.9 between Engelen and Freso and Van Wijnen model. And the Engelen and Freso in non-equilibrium condition was sensitive to change in current speed, suggesting small error in this parameter could lead to significant error in bed level change. This illustrates also the degree of uncertainty in determining sediment transport rate. So after the idealized theoretical channel, I move to the real site, Bank Strait, which is a little bit more exciting. To calibrate and validate the numerical model of Bank Strait, we need in situ data. So with the Austin project, 4 field trips have been conducted in March, July, December 2018, and February 2019. We use a large set of instruments. So the first one here is ADCP, Acoustic Doppler Current Profiler, to measure velocity, and some of them measure waves as well. In the middle with the rocket shape, it's a penetrometer used to test the strength of the seafloor. Then sediment traps I've designed with the help of the technician team to have information about the grain size distribution. At the bottom here, it's an optical sensor with a laser who provide particle size distribution. In the middle here, the sub-bottom profiler to characterize the seabed. And the last one is a grab sampler to have particle size distribution. We also survey the area with a multi-beam. Here you can see a little scheme. To have precise bathymetry in this site. It's very important as an input for the numerical model. And very interesting feature were noticed near Clerk Island. Here it's tidal sand dunes, and with a maximum of 8 meters for the biggest one. Here are also represented all the location of the different stations of ADCP. So the ADCP are looking up for all of them, except just for one. It's the box frame here. So here it's an ADCP who is looking down to have more insight about the bottom velocity, which is important for the sediment transport rates. With the grab sampler, the sediment traps, and the penetrometer, I've been able to characterize the seabed of Bank Strait. So except near Swan Island here, or its median sand, we found in the strait it's more coarse sand around the Clark Island here, and rocky area in the middle of the strait. So this is the part of the characterization of the seabed to be an input for the numerical model. So the sub-bottom survey was compared to the multi-beam survey. So the sub-bottom survey was in December 2018, and the multi-beam were performed in March. So we overlap the two profiles, and you can see it's the dunes are moving. There is a migration, which is clearly seen here. So we need to understand how a tidal farm could influence this migration. So all these data are used to calibrate and validate the numerical model. So I'm going to talk about the model now. Here is the domain. The mesh resolution vary in the domain from 3 kilometers at the boundary here and here to further refine at the approach of Bang Strait. So in the promising area here, the typical node spacing is 50 meters and 20 meters at the location of the farm to put one turbine in one cell. 35-day simulations were run to generate calibration dataset. The model was calibrated against 5 IDCP from the Austin campaign in March 2018, as you can see here. The calibration was achieved by adjusting the seabed roughness. I performed 7 tests to obtain the closest match of surface elevation and depth average velocity. Comparison between model result and IDCP were quantified using the Taylor diagram, and it's using the combination of 3 statistics, the standard deviation, the correlation coefficient, and the root mean square deviation. So here is like the comparison for the surface elevation, and here the depth average velocity. So for the surface elevation, it's the run 4 who is the best, and for the depth average velocity, it's R9 and R4. So we just selected these two, and we compare them in 3D. For the depth average velocity and for the hub height layer. So the hub height layer is where the rotor is located in the water column when we will add turbine. We have also here at the bottom a time series at the hub height. So in black is the IDCP, and in blue it's the result for the 2 run. So the run 4 was the closest to the in-situ data and was selected to represent the best condition in Bang Strait. So after we validated this simulation, and it was run for 1 year and validated against measurement for 3 different periods from March 2018 to February 2019, and we used all the IDCP at different periods. And we use also the Taylor diagram. So all periods show good agreement with slightly lower results for winter, and we just analyze some wave data for this period, and there is a stronger activity in winter, so that explains the difference because my model don't have wave enforcing for now. So after the validation, we had a closer look at the model without turbine, and we could hear the statistical maximum current speed for 35 days. So the maximum velocity were found in the center of the strait here and near Clark Island, with a maximum of 2.4 meters per second. Then I added a tidal turbine in the model. It's 20 meters rotor diameter, and I tested 2 tidal farms, one with 100 and a second one with 300 turbines. So here is the change in the depth average velocity between the baseline and the tidal farm scenario. So for the 100 turbine scenario, the spatial extent does not go beyond 5 kilometers. It's more about 2 kilometers, the same in 3D. For the 301, it's more about 7 kilometers in this direction, and it's the same for the 3D. The difference between 2D and 3D are not significant for depth average velocity. When I had a look at the 3D model, the biggest change in the water column was at the hub height. So here it's the location of the turbine for the farm of 100 turbine, and the same here It's the location where there is the most reduction in the current speed. I extracted some velocity profile to see the difference between the two resolutions, 3D and 2D. So the difference is most significant at the location of the tidal farm. Here you can see there is like a decrease in the flow. So in the 3D model, the decrease of the flow due to energy extraction is well represented in the water column. And far away, so 1 kilometer, 5 and 18 kilometers from the tidal farm, the difference between the two resolutions is not very significant. So this is like for all the current speed. Then I focused on the bed shear stress because it's the principal parameter acting on sediment dynamics. And I compare 3D to 2D as well for both scenarios. So this is the same. It's the change between the baseline and as the case with the tidal farm. So the 3D captures better the acceleration near the bottom at the location of the tidal farm. In the 100 tidal farm in 3D, you can see here the blue and like the white color is an increase in the bed shear stress. Around the tidal farm, the bed shear stress reduction was about 7% for both resolutions, for the 101. And for the 300 turbine, it's about 20% in 3D and 50% in 2D. So reduction of bed shear stress suggests that accretion of sediment may appear and change the dynamics in the channel. The increase here and a little bit here in the 300 suggests that additional score may occur and more erosion could happen at the location of sand dunes. So the location of sand dunes are here, and so the blue color suggests it will be like more erosion. So a closer look was given to the sand dunes region. The profile BB' was extracted for the mean bed stress, and we compared all the scenarios in 3D, in 2D, and for the both tidal farm. Difference between 2D and 3D are not significant, and we can only notice an increase of 0.06 Pascal of difference. So this is a small changes, but it could lead to a significant influence for sediment transport. So to pursue the environmental impact assessment, the focus needs to be on sediment dynamics, to quantify the migration of sand dunes and see the influence of a tidal farm on it. This is my work at this moment, and I'm just implementing the numerical model with WAVE, and I'm trying to reproduce what we've seen for the sub-bottom profile compared to the multi-beam. I try in 2D because we have seen that between 2D and 3D there is not a lot of difference. I'm trying in 2D to run a model for 9 months and to reproduce the migration of the dunes. And after I will implement a tidal farm and determine what will be like the influence on it. So this is the next step for the couple of months. So this project will provide specific data and results for Bank Strait to understand the opportunities in this site and allow regulators and tidal developers to better understand the influence of tidal farm in this type of environment. Like this, in the future, we could be part of blue economy and may have a tidal farm in Bank Strait. This is our future. Thanks for your attention and thanks for listening.
Okay, well, thank you very much for your presentation, Christelle. We have a number of questions, and the first one is from Ray Sayad. He says, it can't be good on sea life, especially where structures provide habitat. There are bound to be a few fishing mishaps as well. I assume that they will need to be located in relatively shallow water.
Yeah, it's shallow water. It's about, so the best site are between 50 and 35 meters.
And do the structures provide habitat, or is the flow around them too significant to provide any real habitat?
No, there is some study, so it's not my field, but I have a colleague who is like looking at this for like the benthic habitat and the relation with the fish and different mammals. And a lot of studies have shown that the foundation of the turbine can provide artificial reef for this community. So it's a pretty good advantage for this one.
Okay. And the other part of the question is, are there likely to be fishing mishaps, or is this all going to be chartered, I suppose, so that fishing boats shouldn't be fishing into any area?
Yeah, I think I'm not sure about this regulation, but yeah, I can have a look at this one, but I suppose that it would be no fishing around.
Okay, thanks. The next one's from Jonathan Binns, who says, quick question, do you have a method of assessing whether a particular amount of sediment transport disruption is too much, or are you really most concerned with quantifying the amount of effect on sediment transport?
So I'm more focused of the difference between the natural variability. So I want to have like my model to reproduce the natural variability of the migration of the sand dunes, and I want to see the influence of a tidal form on it and compare to the natural variability. So I'm more concerned about this.
Okay, thank you. Martin Reynoldson says, I think that it's good that you've been able to show that the 2D model is good enough. Am I right in saying that for this project, the current is always in the same direction, not backwards and forwards?
No, there is like ebb and flow. So I just like show some statistic, and it was just an average I've shown, but there is like ebb and flow, and there is more, like the maximum was in the flood direction. So yeah, no, there is.
Okay. David Stefani says, is there a limit on how far the underwater turbines can operate to supply efficient power to land and therefore limit the influence on sediment loadings on coastal beaches or foreshores?
I'm not sure about regulation, but we try, like the hosting project, try to have like a multi-criteria analysis, and one of the criteria was the proximity to the grid. So to be economic, for the economic feasibility, it's better to have the grid next to the site.
Right, thank you. Jason Samuelson says, how does this research blend with assessing environmental impact of the structures themselves?
Sorry, can you repeat, please?
How does this research blend with assessing the environmental impact of the structures?
I'm not sure if I will fully understand, but I'm doing like a hydrodynamic and sediment transport model of the area, and I validated like the hydrodynamic. I'm doing the calibration and validation of the sediment transport model at this moment. And so when I will implement in the numerical model the tidal form, I will see the influence on sediment transport, and the focus will be on the sand dunes near Clark Island. So it would be like, for me, the environmental impact in this site.
Okay. Martin Reynoldson's chimed in with another one. He says, what would the difference be if the current changed direction with the change in tide?
What would be the difference?
If the current changed direction with the change in tide. Well, I think that the turbines have to spin around and face the other way, don't they?
So in this case, in my model, the turbine are considered to face the flow in each for ebb and for flow. So it changes the axis.
Sure. Jonathan Binns comes with another one. Where do you get the boundary conditions of a few hundred nautical miles off Tasmania from?
So for the tides, I'm using like a global forcing from a global model, which use like it's Topex Poseidon, who have like a lot of in situ data about the tides all around the world.
Okay, thank you. Blago Naskov says, what parameter would constitute a limit to installation of particular turbine power rating, or how the sedimentation may reduce the installed turbine power rating?
So for me, it's first the current speed. In the best side, we have 4 meters by second. In Bong Strait, it's a little bit lower, but it's one parameter who can accelerate or not the feasibility. And after, so where there is like a lot of current speed, we've seen it's more coarsened and rocky area. So it's the typical seabed in this high tidal energy site. So here we have a sandbanks which is located just near the area where there is a maximum current speed. So it could be like a factor of no-go for tidal developer. So the future of my research will be to also look about floating structure, because like this there is like less impact on the sea floor and for sediment transport.
Okay, thank you. Saeed Shairi says, can the modelling of the turbine itself within the mic package be explained a little bit more, please?
Oh, yeah. Sorry, yeah. So the tidal turbine are implemented as a momentum sink. So it's represented as a subgrid object with the influence on the hydrodynamic based on actual distillery. So the influence is modeled by calculating the currents induced drag and lift force on each layer.
Okay, thank you. Moeed Ahmed says, if the turbines are placed together linearly, I think it's meant to be, do they boost each other's acceleration? Do we have any idea yet how the turbines can boost each other underwater?
Yeah, there is a lot of concern about it, and there is a lot of study about the lateral spacing, the longitudinal spacing. And for now, like the preconization to have a lateral spacing of 2.5 diameters and to have, if possible, like between 6 and 10 times the diameter, to have like 10 diameters longitudinally to reduce the effect of different turbine between them.
Okay. And Moeed also asks, would this design be beneficial in providing a habitat for the marine life?
Yeah, so the foundation can be an artificial reef for benthic community.
Hilton Solyom says, when would the Banks project be constructed, please?
I hope soon. No, so for now, the Austin project have a report this year for RINA, and we'll see if like the because there is some industry, there is Mako Turbine from Australia, Sabella from France who are partner in this, and we will see if we have some more funding to continue the study and maybe have a tidal farm in Strait. It would be like, great.
Okay. I think that's almost all. Oh, no, there's more questions coming in. Moeed also says, where can we grab the further information about this project? Can we also contribute to this project?
So there is a website. It's the hosting project. I don't know if we can send the link somewhere. I can provide the link. And after they are on Twitter too. So.
And whose website is it? Can you find it by searching on the web?
Yeah, if you type Austin and Tidal Energy Australia, normally you will find the website with all the news and the different investigators and partners.
Okay, perfect. Saeed Shairi says, I might have missed it, but was there any justification about the effects on whale migration or the like?
So not in my study, it's on my scope. For now, I'm not sure there is for Strait, but for I know for in Canada, in Bay of Fundy, or in UK for the pentland furs, there is a lot of study about mammal migration around future tidal energy site, and they reveal that there is no harm and the whales detect the presence of the turbine and just avoid them. So there is, for now, no danger for them.
Right, okay. Moeed Ahmed says he's found the website. Thank you very much.
You're welcome, thanks.
I might ask a question at this stage. I saw in the blurb for your presentation, or the summary, that there was some talk of work in the Strait above Darwin.
Yes.
Are you doing any work on that, or is that not part of your research?
No, my scope is just Strait, but in the hosting project there is someone who is working and doing the same work as I'm doing on Strait in Clarence Strait. So. I'm thinking that this year you can see some papers on it.
Right. Okay. I have another question from Ian Wiley. Do you have a rule for turbine diameter versus depth at install for minimal seabed disturbance?
So for now we try to have between the seabed and the turbine and the rotor to have a clearance of 7 meters, and after to have at least 10 meters clearance from the water, from the surface elevation.
Okay. Well, if there are no more questions, and I haven't got any more come up, I'll say thank you, Christelle, for your presentation. Thank you on behalf of RINA, IMarEST and Engineers Australia and all the participants this evening.